Yeah, so this is a joint work with Kevin Batz, Adrian Gallus, Just Peter Katun, and Tobias Winkler, who actually wanted to give the talk but couldn't come. But I want to still emphasize Tobias because... sorry? Sorry? Okay, because Tobias and I, we mainly developed this together. So this is also very much his idea. Okay, I want to start with our vision about weighted programming. And our vision is, I want to start with the vision that the probabilistic programming people had. And the probabilistic programming people in some very famous paper wrote that their goal is to enable probabilistic modeling and machine learning to be accessible to the working programmer who has sufficient domain expertise, but perhaps not enough expertise in probability theory or machine learning. Yeah, so the programmers know how to express something kind of in algorithmic thinking, but they maybe don't know measure theory or also just don't care about that stuff. Okay, but I would say not everything is a probabilistic model. And we want to enable more models. So our vision for weighted programming is we want to enable more general mathematical modeling and hopefully also machine learning to be accessible to the working programmer, who has their programming expertise, but maybe not enough expertise in the respective mathematical theory. And maybe they don't even know the mathematical theory, which they are looking for. So we also provide some tools for choosing the right theory. Okay, here's a motivating example, the ski rental problem. I will tell you the scenario of this problem. There's a person who doesn't own a pair of skis, but decides to go skiing anyway for N days. Yeah? And at the beginning of each day, the person can choose between doing one of two things. They can either rent a pair of skis. This costs €1 because they went skiing in, say, Austria. Or they can buy a pair of skis. This costs Y euros once, and then they can go skiing ad infinitum for free. Yeah? Okay, how can we, or what's the question? The question is, what's the optimal, that is minimal amount of money that the person has to spend for their skiing trip? And they want to go skiing every day, of course. And yeah, a programmer might model this like this. I will now go here. So for while the trip is still ongoing, it's N days, we decrement our day counter, and then we can choose between one of two things. We can either pay €1, and then we did this, or we can pay Y euros, and then we set the counter N to 0, because then it doesn't matter anymore. Our ski trip is now paid for. Okay, and our question is, how can we make this sort of modeling a bit more principled and fairly general? So let's look at this problem a bit more in depth. So here we have these payments, and these payments are amounts of money. And usually if we pay more and more and more, then money adds up. Yeah? So in this case, the costs along one path that I can take through this program are added up. So for instance, if I rent for 3 days and then buy, it's 1 + 1 + Y euros. Yeah, and the or, we want to have an optimal amount of money. So the or here should be kind of a minimization over all paths. Yeah, so this should correspond to a min somehow. So if we do either this, rent for 3 days and buy, or immediately buy, then this should be a minimum between these two options. Yeah, and this happens to be a semi-ring. This is the min plus semi-ring in this case. Now, how does one choose the correct semi-ring? We provide we provide kind of a, oh, sorry, I will first show you the syntax of the programming language. So the programming language that we, well, also others have investigated this, but we look at this programming language. It has regular programming constructs, if then else, sequential composition, assignments, and unbounded loops, so potentially unbounded loops, not these for loops or something like that. Yeah, and then we have these two constructs. We have waiting and branching. And the language, the whole language is parameterized by some semi-ring. Now, the question is, how do we choose a semi-ring? And we provide some sort of cheat sheet where the programmer with not so much expertise can look at and then choose the right semi-ring. I give you a few examples. We already saw this. If we want to accumulate costs and choose the branch with minimal costs, and we are in an optimization scenario, then we choose the tropical min plus semi-ring. There's also an Arctic semi-ring where we do a max here if we somehow want to maximize. Then there's other semi-rings. So for instance here, I want weighting A to be that I append some symbol A to the current trace. And branching is I want to account for the behavior of both traces. And this could be, for instance, in a model checking context. And then we would choose the semi-ring of formal languages. So for formal languages, we have all languages, and the addition in that semi-ring is union, and multiplication is concatenation of two languages. So one more example, weighting should be that we make A copies of the current trace, and branching is we sum up the number of traces in both branches. This can be used for counting and combinatorics, and there we would choose the natural numbers with regular addition and multiplication as the semi-ring. Final example, resource usage. If we want A to be use resource A, and the branching is we can use resource A via the left or the right branch, then this gives us the so-called Y semi-ring. You have as universe propositional positive formulae in disjunctive normal form. And there's crazy semi-rings like the thermodynamic semi-ring, the ordinal numbers form a semi-ring. I forgot. There's more, also probabilistic stuff, of course. Yeah. Okay, so this is just there's a very rich selection of semi-rings that one can use here. Okay, if we revisit our ski rental problem now syntactically, then we have here these payments. These are kind of the weightings. So we rewrite this as ×1. And this should be that we incur cost A, or here 1 and Y. And the branching should be a plus in the semi-ring. So, and we can look up in our cheat sheet and see, the tropical semi-ring should be chosen here. All right, so now we have treated our language syntactically. Now we want to give semantics to our weighted programs. So how could we do that? We could give an operational semantics. In terms of weighted automata, we could, and we in fact did. But usually this will be infinite state. And this makes it awful to draw, of course, if not impossible. Also, since it's infinite state, the reasoning about this thing must be symbolic anyway. So I would say this is a very unwieldy and awful object, this weighted automaton, and I personally don't like it at all. So what we do instead, we give a denotational semantics in terms of a weakest precondition style calculus to these programs. And with that, we can just annotate the programs. We can write weighted assertions into the programs. And I think this is much nicer and usually not very difficult. We'll see an example. We can reason about loops using weighted invariants, which I think is also very nice. And overall, I think this this kind of semantics is very wieldy, very nice. Okay, let's get an intuition for this kind of semantics. So here we have the classical weakest precondition semantics. So how does that work? If we have a program C and we have a post condition here, psi, and conditions are maps from states to either true or false. Then here, the weakest precondition will give us a predicate that maps any initial state to whether in the end the predicate, the post condition psi, will be true or not. And we do a slightly non-standard choice here. We say if any of the final states, this is a non-deterministic programs, if in any of the final states the post condition is true, then our weakest precondition becomes true. Dijkstra would put a conjunction here. But yeah, we choose a max here. And now what's the analogon in the weighted world? It's almost exactly the same thing. So along each path, we have weights. Yeah? So with this weigh instruction, we can collect weights. And then we have post-weightings, F. They just put a weight on each final state. And what is now the weakest pre-weighting? Well, we look at all the paths. So for instance, this path gets weight A, B, and whatever F then is in the final states. We collect all these final path weights, and then we do a big semi-ring sum over all of these. And this gives us the weakest pre-weighting. Yeah, of course, this is like an automaton. This is awful, but we can define this inductively on the program structure. So these are the normal roots for weakest preconditions also. But yeah, this is more interesting. So for the if then else, we have here an Iverson bracket. We have heard of these quite a few times over the conference. So this Iverson bracket, if the guard here is true, it basically turns this thing on, and otherwise it turns it off. And turning it off means it puts the whole expression here to the semi-ring 0 or null. Let's call it null, and null plus something is something, and dually for the other branch. So yeah, this picks either the left or the right branch. This just puts the sum, so this really accounts for both branches. The weighting just appends A to the trace, the weight A. And for loops, we have a least fixed point construct. So if we're done, we immediately evaluate the post weight. If we're not done, we recurse on the loop body. And this least fixed point construction also gives us the ability to do invariant style reasoning. Okay, here let's look at an example. This is in fact the loop body from the ski rental problem. And I will push the weighting n plus y. And you remember this is a minimum. So the minimum of n and y I will push through this program. So we have two branches. We have to push this weight to both branches, and then let's see what happens. So first, here this rule will tell us we replace every occurrence of n with the number 0. The number 0 is not a semi-ring null, but it is, in fact, so the minimum between 0 and y, let's say these are natural numbers, is just 0. Okay, then we multiply, and the 0 is the semi-ring 1. So this is a 1, sorry. Okay, next we multiply with y. Now we just get y. Y times 1 is just y. Yeah, and in the other branch, we do something similar. We multiply now with the number 1. It's not the semi-ring 1. Then we combine both branches. We have the y here, and we have this expression here. Yeah, and I will not explain more, but this can be simplified. And we get, again, the same thing. I think, yeah, this shows rather nicely how you can just push an annotation through the program, just like a precondition. But here we have done something weighted. Okay, for loops, how does this invariant style reasoning work? I'm doing on time. I'm doing okay. We have this function here, which is whose least fixed point defines this weakest pre-weighting here. And if we pick an invariant I and we push it through this function and we go down in some partial order, which is on the semi-ring, then we immediately know that I was an upper bound for the whole semantics of the loop. Now, here's again the ski rental example. I want to know what is the weakest pre-weighting of the semi-ring 1. We have already seen that we can push n plus y. This is our invariant, in fact. And we can replace the 1 here and n plus y here. You can do the math and you can see that this is in fact bounded again by n plus y. And so we know that we can put this here, and we know that n plus y upper bounds the whole semantics. And this now tells us, by invariant style reasoning, that the minimum cost that we have to pay here is upper bounded by the minimum between n and y, which is also what we would expect. Okay, now you may know that for weakest preconditions, there are also weakest liberal preconditions. And the weakest liberal preconditions, they also account for infinite or non-terminating behavior. And this is also what we do here. For WLP, we can again define this. All of this is the same, except that for while loops, we put a greatest fixed point here. That's all we change. And yeah, to get some intuition on what happens here, for Dijkstra's WLP, this can be decomposed into WP of F or WLP of false. And this precisely accounts for all non-terminating states. And we can do almost the same decomposition. So for us, WLP of F is WP of F plus WLP of the null of the semi-ring. I think this decomposition is quite useful and shows that all of this makes a lot of sense. The intuition for WLP of 0 or of null is that it's kind of the weight of all infinite traces. In fact, it's a little bit different, but I will almost not go into the details. But here we have the top element of the semi-ring. So there's a little bit more at the end, but usually this intuition suffices. Okay, let's see also an example. I will not show you the calculations, but just what happens. So here's a program. We are now in the formal languages semi-ring. In reality, this is not quite a semi-ring, but a module. So this program can either, in each iteration, terminate and produce an A, or not terminate and produce a B. And the WP for this program is the language B star A. The WLP now also accounts for the infinite traces, so it's the same language, but also this infinite trace B, so B to the omega is also included. And in fact, WLP of 0 is precisely B to the omega. Right, so some case studies we did with this. These are not computer case studies, these are pen and paper case studies. So we already saw the ski rental problem. We used WLP, as I showed you before, to actually do bug detection in a faulty mutual exclusion protocol. So I would like to emphasize that even though we're using WLP and Hoare logic can also be used for incorrectness. So this is, I think the names correctness and incorrectness logic are simply wrong. So we did bug detection. We found that some faulty protocol here exhibits unfair behavior, which we would consider a bug, by under approximating a greatest fixed point. And finally, we also proved some combinatorial identity about Fibonacci numbers using our combinatorics semi-ring stuff. Okay, for future work, this is very much in the direction of my previous speaker. We would also like to find an assertion language for specifying such weightings. And yeah, this should be relatively complete, meaning that if I start with a post-weighting f in that language, then WP of f should also be expressible in this language. Yeah, invariant synthesis for loops would be, of course, a nice topic. Strongest post would be very nice to do for weighted programs as well. Sampling, so probabilistic programming is also very successful because of sampling. I don't know what sampling means here, but it would sure be interesting to find out. Yeah, I would like to know to what kind of measures or whatever these weighted programs correspond to. So what is expressible with weighted programs? For probabilistic programs, this is well studied and well known. Yeah, program synthesis would be cool. So how to determinize the programs, how to get rid of the plus and replace it by some actual if-then-else condition, so that you still get a near optimal or whatever result. And finally, what would also be cool is if we could automatically transpile weighted programs in some theory into a respective solver, like an LP or SMT or whatever solver. Okay, that's it. All I wanted to tell you. I'm happy to take any questions.
We also have an online question if you want to start with that.
Oh, okay.
You want to read it?
Yes.
Take it.
Thanks. So there is a question from the remote audience. This one?
Yes.
Okay. This is a question from Ohad. Cool work. Do you think the semantics can be generalized from a set theoretic semi-ring to the semi-ring of scalars in a model of synthetic measure theory? It may let you also account for probabilistic programming, including continuous distributions. Do you have any idea?
I don't know, but it's sure cool. Yeah.
All right. Question?
Hello, thank you for the talk. That was very cool. My question is, so you said you got a cheat sheet for semi-rings. Is it an ad hoc cheat sheet, or you've got a systematic way to determine what kind of?
No, it's very ad hoc.
Okay.
Yeah. I don't even know how to approach a systematic cheat sheet. But I'm not saying this is impossible, but it sounds extremely challenging to me. No. But
so,
important.
Thanks for the talk. I wonder whether you have seen the S-plus work. Maybe in 2013, there's uncertainty, a uncertain type I think they implemented in C# and use that to capture, for example, uncertainty in GPS measurements, things like that. I wonder whether you have seen that and whether you have any thoughts of, how this line of work can be integrated into more mainstream programming languages, so that, as you said earlier, that more programmers can adopt this programming model.
I'm right now not aware of this work, but yeah. So I want to say we are not the first people to look at weighted computations at all. So what we did, I believe, for the first time was giving a WP and in particular an WLP semantics to this. And our hope with also this cheat sheet is to make this really more accessible and not just put a theory out there and say, we already did this. Now you should use it. Yeah, but if nobody knows how to use it, it's of course completely useless. So it would be nice to look at this and see how this is captured in our framework.
Hi, that was really interesting. When it comes to the synthesis part, have you thought about putting maybe additional structure on the semi-wing? Like saying what happens when you put more structure on the semi-wings? So like special cases?
So what sort of structure are you thinking?
So for example, like I guess in the max example, like taking the max of integers, that's is actually like a sub and a lattice, for example. So that structure might be exploitable for like in synthesis, for
And
example.
so we do need even some structure. So this needs to be in a certain way as an ordered semi-ring.
Oh, okay.
Yeah. We cannot use any semi-ring without structure because otherwise our least fixed point stuff and all of that wouldn't work.
Okay, I was getting a bit confused how you were doing that. Okay, so that makes more
there's
sense.
structure. I didn't present it, but there's structure. Yeah.
Okay, thanks.
Yeah, thanks.
We have some more time for this.
Nice work. Thank you for the talk. So for the ski rental problem, so you have this semantics where you push these weights through the program. And for the ski rental problem, you had to have basically the solution already to this n minimum of n and y.
Yeah, the invariant.
Invariant. But would it be possible to just given the program find this optimal solution already, or does this already go to this future work to transpile it to LP?
Yeah, so maybe the translation would be a way to actually find invariants when I then offload this to a solver. But yeah, semantically, the stuff is well, I'll just use this now. Semantically, it's well defined. It's the least fixed point or greatest fixed point. And then it's like for normal programs. If you want to prove them correct or whatever correct means here, you have to guess an invariant or synthesize it or find it or it falls from heaven somewhere. Yeah.
So would it be correct to say that the optimization problem that you encode as a program to solve this optimization problem corresponds to finding the invariant?
I would say the optimization problem itself, together with the post-weighting, describes the program together with the post-weighting describes the optimization problem. And doing WP is a solution to the optimization problem. So
very interesting.
Okay, so let's thank the speaker again. Thank you.